So are you able to see the screen?
Yes, sir. Yes.
Okay. So in the last class, I left you with this question. So can I know what is the answer for IT? Can somebody tell me that? What will be the answer? One student was telling me, right, the answer for this. Yeah, recording is already started. It's there, so it's already we are recording. But somebody was telling me the answer for this question. So where is that student?
Actually, sir, I am asking for the previous one, not for this. I am want to
Oh,
recheck that answer.
oh, you wanted to recheck the answer. Just a second. I will see that. Which answer you wanted to check?
Last one is the previous one. This question.
This question?
No, previous
Okay.
one of this.
Okay, this one, eh? What answer you wanted to check for? Like in this case?
My question is same as you got, but my answer is coming 17.39 angle minus 118.2 degree.
एक minute. 17.39 angle
Minus 118.2 degree.
that we have to see actually. I think did I solve this question? Okay, I gave you the answer. Okay.
Yeah.
Maybe your calculations are wrong because I checked it from the book actually. So this answer
Yeah,
must be right. So you just try again and see. Oh, the screen is stuck. Just a second. Huh? I don't know why it's not showing up. Just a minute. Okay, I'll just stop presenting first. Let me. Okay, are you able to see the screen now?
Yes, sir.
Okay, so maybe you can cross check the answer because I already saw this from the book, or maybe some other students, if they are getting the same answer, then we can say, okay, I made a mistake. But I guess answer is this one only. Okay, try to see.
Okay, so I will recheck my.
Try to check again and see whether you have made a mistake or not. But definitely, in terms of polar computation, maybe you are still making a mistake. So be comfortable in doing that, and then I guess then it will be solved. Okay.
Okay, thank you.
Okay. So how many of you have solved this question which I have given you? Anyone? This one? No one has solved?
Sir, can I answer?
Yes, please.
So is it 0.4 angle minus 116.4 degree?
Just a second. I will check it with my solution. So your answer is, what you are saying is 0.4
Minus 116.4 degree.
No, this is not the right answer. This is not correct. Anyone else?
Sir, is it 0.89 angle 26.57?
Yes, but the sign will be there, right? Minus 26.56.
Yes, sir.
Right, so the correct answer is 0.89 angle 26.56. So only two people have done it, not others. So maybe let's have a poll here, like how many of you got the same answer. Can you raise your hands here on the chat window in case if you have done it, so that we can net. Okay.
Sir, done it but got a different answer.
Okay. Okay, 35, 54. So you two people, okay, so many of you have done it. But answers, are you getting the same answers? The one which is shown? Okay.
Sir, I am having a little problem in converting that into this phasor form from the user form to phasor form.
Okay, what kind of problem are you facing?
Like I get the answer in terms of J, then I don't have a scientific calculator right now, so I'm having a trouble in converting to this type of answer.
Okay, so what you can do is, let us say you get this answer, right? A plus JB, right? Okay, so what you can do is you mentally can, you can have this picture in your, mind like this. So if you have mentally this picture, then this thing you can calculate, right? In calculator, like square root underscore a square a plus b square. This can you can do, right?
Okay.
And then you can divide b by a and take tangent inverse of that. So that one can be done by a simple calculator also. Then there is no need. Okay. So try to make a mental picture like this and then solve it through a calculator, normal calculator. Okay. Okay, so many of you have solved it, but still, some of you still, I think, found it difficult, or maybe you were not able to solve it because you have not done so many exercises by your own. So let me tell you like how to solve this question, so that everyone will be comfortable with how to solve these type of questions and get a command on this. Let's do one thing. We have to again convert this into polar format. Okay, in frequency format. So if I want to convert this into frequency format, then what it will be? Just a minute. So how will I represent this source in polar format? It will be tan angle 0.
0.
Okay. So it will be tan angle 0. This thing, it will be bold I. Okay. What about this? It will be 1 by j omega c. 1 by j omega c or not? Right? So it will be actually, so if you want to get this answer, then what it will be?
Minus 10J.
Okay, let us keep it like this to avoid confusion, because sometimes we have to do some cross multiplications and it will be a problem. So let me keep it like that only. And this one will be j omega L.
J omega L.
Okay, and this is 5 ohms. It will remain the same. So now what we will do, we will actually apply we will apply nodal analysis here. And the thing is, what I will do is I will use let me put this here. So this is the first node I will take, V1. This is the second node I will take, V2 here. Okay. So if I take these two nodes, this will be, everyone will agree that this is 5 omega plus j omega L. We can write like that. So yes, this will go away. So we have added it like this. So it will be 5 plus j omega L. And how about this one? The one which is on the bottom part, this 5, we can write it as what? We can write it as 10 omega parallel with 1 by j omega c. Can we write it like that?
Yes, sir.
So if we can do that, then if you evaluate this expression, the one which is written over here, this expression will come out to be what? This expression will come out to be, let me write it here. So it will be like this, and it will be 5 minus j5. Please cross check this if you are getting this answer. And this is 5 plus j5. So this is removed here. So ideally it should be not be this, it will be again a box like this. We call this as Z1 we call this as Z2. And why we are writing this box here, can anyone tell me what's the reason?
A combination of.
Right.
Combination is
Yes.
not only resistor.
Right, so it's a combination of resistance and capacitance and or resistance or inductance. So it's a complex impedance, so we write it by a box here to represent that. So this is the parallel combination of the capacitor as well as the resistor, and this one is the series combination of the resistance and the inductance. Okay, so this is one thing. Now what we want to do is we want to apply which kind of nodal analysis we have to do here, like which case it is lying, like if I use V1 and V2 here, what can I do, like which theorem we can use? Good. So this is super node case, and so in this super node analysis, if I want to write for the super nodes, I will write like this. It will be V1 1 by 10 plus 5 minus J5 plus V2 by 5 plus J5, and then what else? Then we will have minus 10 angle 0 divided by 10 equal to 0, right or not? Any problems here in understanding this? Anyone having any problem in understanding this? Let me know this equation.
No, sir.
So this is what we are doing. We are actually using a graph. We are creating a Gaussian surface here, and then what we are doing, we are actually calculating how many currents are leaving this surface and how many currents are entering in this surface. So we are actually writing this equation for that Gaussian surface, which I have already told you so many times for the supernode case. And the second equation will be to relate this V1 and V2 using this controlled source. So if I write that one, it will be V1 plus 10 IT equal to V2. Will it be or not? Because there is an uprise in the voltage, so you are going from V1 to plus 10 IT equal to V2. So this is the second case. Now if I want to write IT, so let me write this also. I made a mistake. It should not be IT here, it will be bold I. And why?
Because we are talking in frequency.
Yes, we are talking about phasors, right? So this is I, right? So this will also change to bold I. Okay. So your capital I or bold I is nothing but 10 angle 0 minus V1 divided by 10 ohms, right or not? So this is just simple, right? Current is flowing in this direction, and note, you cannot change this current direction, right? It's already defined for you. If it comes out negative, this polarity will change. So this one I have already indicated you earlier, so please note that. So if the question is giving you the direction, you cannot change that direction because your controlled source is defined using that direction. So if this direction changes, the polarity also change. So keep that in mind. So do not change the directions of the given currents which are already there in the in the diagram, provided they are controlling the control source. If they are not controlling the current source and if we are still giving you some direction, then you are free to change it. So you can okay, this one will also be bold I. So now it's very easy, right? You can actually substitute this I here. So you will get equation between V1 and V2, and once you get V1 and V2, one equation, and this is the second equation where you have V1 and V2 as the second part, and then you can easily solve for V1 and V2 because you have two equations and two unknowns. So once you solve for two equations and two unknowns, the value of V1 that you will get here will be 4.47 angle 63.43. So this will be the value of V1 that you will get. For V2 you can calculate yourself, but there is no point in calculating it because you want to calculate current I, and current I depends upon V1. So we want to know only V1 only. There is no point in calculating V2. So once you have V1 calculated already here, then you can actually substitute it here and get the answer. So now the important thing is this is in polar format. Either you can take it as 10, because tan angle 0 is nothing but 10 plus j0, so there is no point in it's easy, right? So what happens is, this is the subtraction part, right? So polar format will create troubles here. So you have to actually convert it into polar format. So the polar format here for this particular case is, I guess, it's 2 plus 4j, I guess. You can check it out. So this polar format, once it's there, you can subtract and get the answer for the current, and the current answer will be 0.89 angle minus 26.56. This is the current that you will get for this. So any questions here related to this question? So everybody is comfortable with this question? Okay, so if you are comfortable, let's do last question for this particular topic on circuit theory, and then for AC analysis, and then we will move to the next topic. So let me give you last question for this particular class, and we will solve it using two different approaches, so that you will get to know how to do it through two different ways if we want to do it. So let us say you have this question, 3 ohms to So in this question you have to find the current here, ILT, this one. So this is the question, and can anyone tell me what kind of approach will be best here? Right. So now I guess you are getting a feel of by seeing the circuit which one will be suitable. So that comes only when you practice. So that's what I was telling you when we started off with this course. So it's good that you realized that by observing the circuit you can do some wonders and see whether you can do mesh analysis or nodal analysis or which kind of which kind of theorem you want to apply here. So that's good that you understood it. But you solve it through mesh analysis, then we will solve it with some other technique also, which I think you are missing. So we can use that technique also here, and it will ease out your life. It will make things much simpler as compared to the mesh analysis, because you can see the amount of effort that you will be putting in here to write the mesh equations. So I'll give you a few minutes to solve this question and let me know what will be the answer in case if you can solve it, and then we will then we will move forward with some other things. So let me give you, right now it's 8:55, so I'll give you 10 minutes to solve this. Try to solve it and get the answer for me. Okay. Yes.
I got the answer.
Yes, please tell.
1.50 minus J 1.27.
1.50. Then, okay, you are telling in Cartesian coordinates, eh?
Yes, sir.
So can you convert it into polar?
Sure.
Yeah,
Give
just
me a minute.
yeah. So, meanwhile, how can you tell me how can I write this one in polar format? Anyone?
12 angle 0.
Right.
12 angle 0.
Right. What about the other source? This one.
6 angle 90.
Angle
6 angle 90.
Will it be 90 or minus 90, right? It will not be.
minus 90.
Right, good. So it will be 6 angle minus 90. Please note that it's very important, because if you make mistake here only, then everything will go wrong. So try to check that. And if I want to write this, then it will be 1 by j omega c, and 1 by j omega c, if you evaluate, its value will be minus j4. Okay, and similarly, if you want for the inductor, it will come out to be 1j plus j, right? And this one we can write as minus 6j also. Okay, both are right.
Sir, I converted.
What's the answer?
1.96 angle minus 40 by 25.
40.25. You are close, but I guess maybe some approximations or some problem. But my answer is this one. I will tell you 1.17 cos 1000 t minus 46.5 degrees. Check it out. Like, maybe you made some mistake while doing the calculation. So this is the current ILT. Okay, so we will solve it, don't worry. So let us see through two different approaches. So the first approach is, as you all told, the first approach is mesh analysis. So what we can do in mesh analysis is we can assume a bold I1 here, bold I2 here, and bold I3 here, right? So if I do that, then you can easily write the equations, right? There is no problem here. Like for this first loop consisting of this one here, what we can do, we can write as minus I1 3 minus j4 minus 2 I1 plus V1, then we have minus I1 minus I2 times 2 plus j1 is equal to 0. Is it right or not? Can anyone tell me? Right? This is for loop 1. This is loop 1. This is loop 2. This is loop 3. For loop 2, if I want to write, it will be minus 2 I2 minus 2, sorry, not minus 2 I2, just a second. It will be minus 2 I2 minus I3 minus 2 I2 minus it will be plus 6j.
Sir, in loop. Sir, in loop 1 minus 2 I1 minus I3. Yes.
Okay, yeah. Right, I understood. Yeah. In loop 1, it will be minus 2 I1 minus I3. Good. So this is this one. So the second loop equation is correct. Loop 2. Just check and cross verify with them. Or it will be, it will be right. Yeah. Is it correct?
Plus 6j into I2 I.
Plus 6j into 6j, why it will be multiplied with I2? It's a voltage source, right?
Yes, sorry.
So equation is correct. If you are not answering, then I am assuming the equation is correct. Okay. Okay. For loop 3, I am writing on the top because I don't want to copy and paste again. So in loop 3, it will be for loop 3 it will be 2 I3, then we have minus 2 I3 minus I2, then we have minus 12 angle 0, then we have minus 2 I3 minus I1 equal to 0. Let me know if this is right or not.
Yes, sir. Right, sir.
So now I guess it's easy, right? Because you have three equations, three unknowns. You can write. You can actually do one thing. You can collect the I1, I2, I3 terms. So if I can write this loop 3 equation as A I1, let us say B I2, and C I3 equal to 0. So we can represent this in the matrix form like this: I1, I2, I3 equal to right side. For this loop, let us say it is A, B, C here, and then you will have 0 this side. And for loop 1, for this loop 1, again you can collect the terms for I1, I2 and I3. Then you will get something like D I1 plus E I2 plus F I3 equal to minus V1. Why minus V1? You can check that this is the constant which is going on the right side. So it is minus V1. So if I write that one here, so it will be D, E, F, and then here you will get answer as minus V1. For the third one, again, there is no constant involved, or is it involved? Yeah, it is involved here. So, yeah, so it will be minus 6j here, right? And then you can collect the terms for I1, I2, I3 in the loop 2 equation also. Then you will get GHI. So the corresponding coefficient, yes.
V1 also, sir. V1 in place of 0.
In place of 0 here. Yeah. Sorry. Yes. Right. It will be 12 angle 0. Right. So this is the equation, and I hope you can collect these terms for I1, I2, I3. You can, I'm calling these coefficients, the value A, B, C, D, E, F, G, H, I, and then you can easily calculate the corresponding currents out of it. And once you get the currents, then you want to calculate this one. Then what will be the value? Can you tell me? Like if I want to express this in terms of I1, I2?
I1 minus I3.
Right. So your ILT is nothing but, not ILT, rather it will be bold IL equal to I1 minus I2. And then once you get this answer will be converted into rectangular or polar, whatever format it's given, and the answer will be 1.17 cos 1000 t minus 46.5 degrees. You can cross check later on if you are not able to solve it now. Then we will see, and let me know in case there is some error or not in this particular calculation.
2.69 angle minus 124.
Which one? The current value you are selling?
Angle minus 124 degree.
No, this is the answer which I am giving you here. Okay. So there is no other answer, right? Only one answer will satisfy this thing. So yes.
I have a doubt.
Yes.
When we write for loop 2,
Huh.
do we have to see the positive and negative sign of V2 because it will be AC current.
For this one here?
Yes, yes.
No. You have to actually, because this is the plus minus we are taking as a convention, right? So okay. Okay, now what I'll do is I'll take this again. I will tell you another way of solving it, which will be a bit easier compared to the one which is given over here. So if I tell you that I can solve this using nodal analysis, how many of you will agree on that? Like we can do it through nodal also.
Yes, sir.
Can be
By
done.
giving three different nodes in that. Three nodes.
Yeah, that one. Yeah, that's right. Yeah, this can be solved using nodal because you can write V1 here, V2 here, and then you can write V3 here, right? So nodal analysis can be used, but can we simplify it further? Like, can we do some simplifications to solve the circuit in a much better way? Can anyone tell me?
Source transformation.
Yes, good, very good. So we can do source transformation here. So this thing you can convert into a current source in parallel with resistance or not? Can we do it? So what will that be? It will be it will be a current source like this. What will be the value of this current source?
6 angle 0.
6 angle 0.
And what will be the resistance connected here in parallel to this? It will be 2 ohms, right? So we can remove this, right? Can we do or not?
Yes.
Yes, sir.
Okay, and how about the other one? This one, can we change it also or not?
Sir.
So
Yes, sir.
so this will be it will be a current source going like this. Let me erase this here. So it will be a current source like this, and the value of that will be minus J3 amperes, right? And then we can remove this. This is the parallel resistance to it. So this is a much easier way of solving it. Now you can use nodal analysis here. So let me write the nodal parts for this. So in case if we focus on V1 first, then we can write like this: V1 1 over 3 minus J4 plus 1 over 2 plus 1 over 2 minus V2 over 2 minus V3 over 2 equal to minus 6 angle 0. How many of you say it's right if I apply nodal at this point and if I am writing this equation?
Yes, sir. Yes, sir.
Right? So you can get this answer using nodal analysis. For V2, if I want to write, it will be V2 1 over 2 plus J1, then we have 1 over 2, then we have 1 over 2 again, then minus V1 over 2, then minus V3 over 2 equal to 0. No, it will not be equal to 0, it will be 6 angle 0 here. Is it right?
Yes, sir.
So what we are doing, we are actually, again I am telling you 100 times this thing, already told you so many times, but for every node we have to actually calculate the currents leaving that node and how many of the currents are entering into the node. So these equations on the left are currents leaving the node, and this one is the current which is actually entering the node. So that's why it's on the right side. So this is for V2. For V3, if I want to write, it will be what? It will be V3 1 over 2 plus 1 over 2 minus V2 over 2 minus V1 over 2 equal to minus J3. Will it be or not? Or
There will be one more cycle.
there will be one more half.
Okay.
Is this correct?
In D, like V3
Yes.
V3 to the ground.
There will be one more half, right?
Uh,
Right. So any questions in understanding this, please let me know. I think you can do it, right? It's not a big deal here because now I think you are proficient enough to write nodal analysis and all these stuff. So now will you all agree that you have something as a matrix here with V1, V2, V3 and something here as I1, I2, I3. We do not know whether these values are, you know, zero or whether they are, you know, a proper current sources. So you have to keep them as per the right side of the equation, and once you solve for V1, V2 and V3, then you know that you want to calculate ILT, and then ILT is nothing but V2 divided by 2 plus 1j. So ILT is nothing, or rather not ILT, it will be bold IL, it's nothing but bold V2 divided by 2 plus 1j. And V2 you can already, you know, easily calculate using this equation. So once you solve it, you will get that same answer which I have given you. And the answer is, let me write it again. So it's 1.17 exponential minus j 46.5. And if you want to get the current in the time domain, then you operate real part on this and you will get 1.17 cos 1000 t minus 46.5 degrees. So which method is simpler, this one or the earlier one?
Last one.
So you can see that, you know, by making use of some transformations, some theorems, how can you simplify your life? That is the main objective of this course. So answers will come out to be same from any method, whatever you use. You can use your tricks, you can use any method, whatever you want. Answer will come out to be this only. That is the first, beauty of this circuit theory thing. And the second thing is, you have to train your mind in a way to see, like, what kind of theorems you can apply to simplify your life, which you have studied so far. So that is the only trick to, solve these questions. So that can be solved through various methods. Nobody is stopping you from that. But the main thing is how to come up with a faster way of solving it using different approaches which we have told you. Until unless we tell you to solve it through a specific approach, then it's a different issue. But if we are not telling you, then you can use your own intuitive, mind, and you can apply your, own mind to see how you can, use which method to simplify the things. Okay. So any questions into these questions, like, whatever we have discussed so far? So,
Yes, sir. How can we solve the three complex equations with the help of scientific calculator only?
with the help of calculator?
Yeah, three complex equations we are getting, not a simple one, actually.
Actually, I think, in calculator, if you want to, are you asking me to, use calculator and how to solve it through that? Are you asking me that question?
No, I am asking that we are able to do the three complex equation solver in normal scientific calculator?
We can do that. Actually, in scientific calculator, we can feed the matrices also. So you have to study that manual for that calculator, and in that you can easily feed in the coefficients of these matrices, and then you will get the answers for A1, A2, A3. So in
Manually we are not able to do, no?
manually you can do, but it will take time, right? It will take time. Actually, in calculator we have this option of feeding these coefficients here, this one and this one. So you can feed these values and these values, and they will give you this values V1, V2 and V3. So they have this option. So you can check before purchasing the calculator whether they have this facility of matrix thing or not. Okay.
Thank you.
Okay, so with this, we finish off with the AC analysis, and I think I have done so many questions related to that, and I'm hopeful that you will also feel confident once this particular topic is finished. And one thing you must have observed also, that most of the theorems which I was already telling you so many times, they are already applicable to this particular AC analysis with the only minor differences which you know now, like what are these minor differences. So once we have covered this, now we will be moving on to the next part of this course, which is basically called as transient analysis. So if you recall, uh, in the first part of this course we did DC analysis, where the voltage sources are having a fixed value and they are not moving here and there. Like if I am applying a DC voltage of 5 volts, it will always be a 5 volt and it will not change. Then we moved to AC analysis, where you had changing voltages, and we saw how to tackle these type of changing voltages using phasors, and we tried to gain some insights how to solve these currents and the voltages corresponding to that. And we also saw that the frequency that we are dealing with in AC sources is fixed, we are not changing it, and most of the current and voltages which are flowing in the circuits will also be following that same behavior with same omega which is flowing over there. Okay, so we saw these two type of analysis. The third type of analysis which we have is called as transient analysis. In transient analysis, what happens is, first of all we have to learn that what this transient means. So this is very important. Like as we are saying transient analysis, we do not know what transient means. So let us first of all understand what this transient means, and once you are comfortable with this particular term, then we will understand the later part of the concept which are involved in this particular topic. So transient is basically a phenomena which happens when you move from one situation to another. So let me show you that situation. For example, if you have a voltage source V, which is a DC voltage source, and then you have a resistance like this. This is just I am cooking up this example, but just to show, or just to tell you like what exactly this transient means. So we have normally in transient analysis we have these switches now coming into play. So these switches, what happens is they have a property that if you move this switch down, then what will happen? It will connect these two circuits by a short wire. So it's a short circuit switch. So it's basically you can say it's a short wire, and I have already told you the property of a short wire. So if you connect this wire to this, then the circuit is complete and current will start flowing. But if you unplug this towards upside, then this circuit will break and there will be no current flowing in it, because the loop is broken. So if the loop is broken, there will be no current flowing, as I think you must be, you can also visualize yourself that if there is no point connection in between the 2 points, current will be 0. So there will be no current. So this is the property of the switch. So what happens is, in the earlier cases when we were doing DC analysis, at that time the voltage was constantly applied to the circuit. But now what happens? Now voltage is applied suddenly. So it's like if you see this switch, what happens right now? If I assume the voltage across the capacitor is 0, let us say, then at this point there is no current flowing into the circuit because switch is not closed. But the moment switch is closed, what will happen? The voltage will become capital V or not? The voltage which is applied onto the circuit will become capital V. So if you want to plot with respect to time the voltage which you are applying onto the circuit, if you want to check that, then will it be a unit step or not? How many of you will say it's a unit step? Because we are actually putting a time t equal to 0, let us say. We are putting a time t equal to 0 means we are switching on this switch at time t equal to 0. So at time t equal to 0, which I am calling here, then earlier at time t equal to 0 minus, that 0 minus means nothing but a very point close to 0, but we are calling it as 0 minus. It is very close to 0, and you cannot distinguish between the two. They are so close, like the difference between 0 and 0 minus is, let us say, 10 to the power minus 14. So it's so close. And there is another point which we call here as 0 plus. So the difference between 0 plus and 0 is nothing but it's 10 to the power minus 14. I'm just cooking up this number just to tell you that they are so close. So, but what we do is, in transient analysis, we distinguish between the three. We say that 0 minus is different from 0 plus, and there is a boundary in between that, and the boundary is 0. So can you tell me, at 0 minus, what will be the voltage here in this circuit? Like, will there be any voltage?
Zero.
It will be 0, right? Because the voltage source is 0. But the movement at time 0 plus, it will be plus V or not? So it will be plus V. So what is this function? Can you tell me what is this function? We have already discussed this.
Unit.
Right. This is unit step, right?
It should be unit step, no sir, because this capacitor is not charged instantly.
No. See, the thing is, I am not talking about the capacitor voltage right now. What I am talking about is, let me draw in the other way around. I am not talking about the capacitor voltage. I am just talking about at this voltage, at this point. Let us say this one, V1. I am talking about this V1 board. Okay. I am not talking about this capacitor right now. I will talk about it later. But right now I am talking about, if you want to check at this point, will this be the correct waveform or not?
Yes sir.
Right. So this is actually V1 here. So at time t is equal to 0 minus, we have no voltage applied. So here it will be 0. But at time t is equal to 0 plus, the switch is closed at time t equal to 0. So at 0 plus, so that is just after the switch is closed, the voltage V1 will be equal to capital V. And this is like a unit step. So now you have a unit step type of thing. Please recall, in the earlier situation, when we were dealing with DC voltages, we do not have these type of phenomena. Like, in time, the DC voltage was like this only, constant throughout. It was not changing. But here what we are doing, because of this switching action, we are creating a switch here. Like, we are creating a abrupt discontinuity. So the voltage here is different from the voltage here. So that's why this transient analysis comes into play, because you are trying to solve the currents and the capacitor voltages under this transient, under this time domain analysis, because at time t equal to 0 to the left we have different voltage, at time t equal to 0 to the right we have different voltage. So our currents and voltages will change. So let me show you one example here. So what will happen is, if you plot this current IT, earlier when there was only DC voltage, at that time your IT will come out to be, let us say, V by R, V by R plus, you have to solve this C. I am not trying to, give you the complexity of this, but let us say you write it as ZC. So at that time, your current will be V by R plus ZC. So it will be a constant current. It will be a constant current in case of DC voltages. Please note that this C is somewhere, I am trying not to confuse you here. Let me remove it and put a, I think I have to, because, but what I was trying to explain here is that, once you apply this switch, what will happen is your currents, it will start oscillating. So your currents will behave like this, Let me show you that. So somewhere it will be like this, it will be doing like this, and it will settle something like this. So I wanted to, please do not confuse this with this experiment. Like, do not keep in your mind that you have R and see how it is behaving like this. What I am trying to tell you is this factor transient, what this transient means. So in that sense, what you can see now is, like, as the voltage is changing, as the voltage is changing, earlier the voltage was not changing, now the voltage is changing. Because of that, you have a sudden, this type of activity which is coming up, and then it settles down to a constant value. So the important point is, what is this called? This is called as transient part of the circuit. This is called as transient part, and this is called as the steady state part. Steady state part. Why this transient part is coming? This transient part is coming because your voltage which you are applying, actually it's going up like this, and then it is getting to a constant value. So because of this going sudden up here, this is the transient, this is creating this transient phase, this fluctuation which is going from 0 to 1, this is creating this transient phase, and you can see that this transient phase will die down after a small time. This will take few seconds only to die down, and after that it will give you the same value which you will get from the DC analysis. So if you solve for the circuit for this DC voltage, whatever current you will get for it, that is the value which you will get here, and this is the steady state value, and this is the transient value. And this transient is coming because you are actually creating a switching action here. The voltage is going from 0 to some value, that's why this transient phenomena is happening. So now we want to understand this transient analysis when your voltages are switching like this. Any questions here related to this? Anyone?
There won't get discharge.
No. See, I was telling you before also that this capacitor, you forget it right now. You just think that it's a circuit here, a complex circuit. We are not going into the details of this complex circuit, but what we are interested in to see what is the currents and the voltages, how they will behave if your voltage is switching like this. So I was trying to explain you that. I am not saying what is the capacitor voltage, what is the current flowing. We will discuss this in a while after this explanation. But what I am trying to make you understand is that if you have a circuit, let us say like this, a complex circuit, we do not know what's there inside. I am not interested in that. What I am interested in is that we have this voltage source, a DC voltage source, and if I make a switch and make it close, earlier there was no DC source and now I am closing it. So the voltage at this point is becoming like this as a unit step. So I want to see that if I apply a unit step like this, how will the currents IT which are going inside this network, and how the voltages VT which are in this network nodes, the complex network nodes, how they are behaving. So what we saw is, if the currents we will try to plot, it will give you something like this, some fluctuations, and then it will settle down. And for the voltages also, it will have some fluctuations and then it will settle down. So we observed that earlier in the DC analysis. What happened in the DC analysis? You used to get same I throughout for all the T and same V throughout for all the T. But now what you are observing is that you are getting these values later on. These values you are getting later on. But before that you have some fluctuations going on this side. And this fluctuation is because of the transient switching that you are doing because of this switch. So we want to understand in this particular, basically for the coming lectures, that when you do this switching, what kind of behavior it will create for this IT. So this you can call as steady state value because it's a DC value and DC was not changing. And so now what happens is, this particular IT is broken into two parts. One is called as steady state value, and by saying steady state value means now your DC voltages are settled down. So you can observe that your DC voltage here is settled down, right? It's settled to a specific value. So this corresponds to this steady state value. But at this point the DC is not settled. It is going up and creating a discontinuity here, right? So voltage earlier was 0 and it suddenly moved to a voltage V here. So because of this, you have this phenomena which is given over here, and we call this as transient phenomena. So when you try to solve the answer IT in case of transient analysis will be transient part plus steady state part. So it will be a combination of both, and you will soon see that this transient part will become zero immediately after a while. So it will consist of let me give you an example. It will consist of some exponential term like this plus cos omega t, something like this. So from here you can see this part is a transient part. As you can see, when you increase t tending to infinity, then this part will go 0 or not, whereas this part will still remain because it's a cos omega t, so it will still be there. So this is the steady state part, and this will be the transient part. So we will see when we will solve. Yes.
We are changing the voltage. We are taking unit step, but if capacitor is there in the network, then dVc by dt will change
Yes, everything will be right. We will understand that also. See, that's why in order to avoid the confusion, I told you to forget about capacitor right now. You just keep in mind that it's a complex network, and what we are understanding is we are understanding only the IT and VT of this complex network. We are not going into the details right now. We will go into the details in the next class, and we will understand every details of it. So right now you consider it in that way, that it's a complex network and we are only interested in how this profile of IT and profile of VT will behave. Earlier profile was constant, but now it is transient plus constant. So for this class it's more than enough for you to understand this. So if you have any doubts in understanding this concept, you let me know. Otherwise, if you have anything other than this, like what will be the change in the capacitor or inductor and all that, then please wait for the next class. We will discuss it in more details at that time. So let me know if you have any questions in understanding this. Yeah.
Sir, that cos omega t, but there is a constant when it is in steady state. So why cos omega t?
No, see. Yeah, you are right. This will be, a B factor. Right. Good. Because here we are actually going for DC analysis, so it will be B times some voltage or something like that. Yeah, it will be a constant. It will not be cos omega t. Yeah.
Out in that line only, sir. Sir, we are writing e to the power minus t, sir. Then it would not turn to be constant, no, sir.
No, it will not, because with time as you progress, the exponential part, right? How it behaves. It goes like this, right?
Yes, sir.
So it will die down.
Okay.
So we will explain you with more concepts, but in the DC analysis, as I'm telling you, you will always put this voltage constant. But now there is a abruptness in the voltages. So we are trying to characterize these abruptness. Like if you switch on or switch off, that is something like you are applying a unit step to the network. So we want to understand that if you apply a unit step to this network. So let us say if I do not put a switch here, and if I apply a unit step like this, will it be performing the same way as I was telling you earlier or not? Like this is equivalent to this particular thing is equivalent to just a minute, I'll draw another slide. If I write, you have a voltage source with this unit step, and this is the network, is equivalent to a voltage constant VDC and a switch. Will it be or not? Are they both same or not?
Yes, sir.
Right? So that is why we want to understand that if I apply a unit step to the network, how this currents and voltages which are going inside this network, how they are behaving. So we want to understand that from this particular type of functions. So once you are comfortable with these type of functions, then you can easily do it for any arbitrary functions like this. So if I apply a triangle wave into this wave in this input, then you easily know that how to write this triangular waveform in terms of the ramp functions, which we have already discussed, and how ramp functions can be represented in terms of the unit step functions. So the main idea is to understand how these currents and voltages are behaving with these type of signals, which are, you know, square, ramp or triangular, which we had already discussed. That is the main idea actually. So we observe that if you have these type of signals with the, you know, abrupt discontinuity or having a slope like this, then your currents and the voltages will behave with a transient followed by a steady state. It will be like that. Okay. So are you getting the point? Like where we want to go for, like in this particular topic? Are you getting the motivation for this? Like why we are going into this? Okay. So that is the motivation part for entering into transient analysis. So in the next class we will go into more details about what will happen to the capacitor, what will happen to the inductor if it is there, how they will behave, how to write differential equations and how to solve them. So we will go into that in the next part. Okay. So if you still have any problems related to understanding this, please let me know. Otherwise, you know, it will be difficult for you to, you know, go further if you do not have this concept clear. So note this point, it's very important. So whatever I have discussed related to the switching also, like, you know, so what normally happens is you actually take time t is equal to 0 to be the time when you close the switch, and time t equal to 0 minus, so we have this boundary 0, then you have 0 plus, then we have 0 minus, and then we have plus infinity, and then we have minus infinity. So we have these different time points onto the scale of time here. So what we do is when we have this switch over here, and if I close it at time t equal to 0, that is the point which we are indicating here. And we want to see the behavior of this switch after behavior of the circuit after that time t equal to 0. So we are indicating it by 0 plus, and the difference between this is 10 to the power minus 14. Similarly, the difference between that is 10 to the power minus 14. So 0 minus is basically a situation where switch is open, and whatever circuit we have at that time, it is corresponding to 0 minus and between minus infinity. So if you have a circuit which is like this, so the state of this circuit is actually here between minus infinity to 0 minus. But the moment when you close this switch, it is basically at the point 0 plus you are looking, and once you keep it closed for a long time, then it means you are in between 0 and infinity. You are in this place. Are you getting the point? So there are few distinctions. This is the one. This is also called as steady state, because you are already in between minus infinity to 0 minus, and your circuit is like this. It is open and it is always there, you know, there is no change here. It's from a very long time it is like this. So again, this type of situation is also a steady state situation, because your switch is not closed and you are actually here at this in this region. But the moment at time t equal to 0, when you close this switch, what happens? You are in this phase. You are in this phase, this phase. This is the transient phase. So once you close this switch, then from here to here, you are again in the steady state. And note, that this is the transient state, right? At this point only you will see these fluctuations, and after that these values correspond to this region from 0 plus to infinity, and this is basically from 0 to 0 plus. In between 0 and 0 plus you will find this transient simulations, and because this range is 10 to the power minus 14, that is why this will actually also die down in a very short period of time. So we want to understand all this in our next class. Okay, so any questions here related to this? So yeah,
It is a very short period of time, so like, what is the need to observe that changes? Can't we neglect like we used to do in ideal case?
no, because actually what happens is, it's a very good question. The problem is, these transients, what happens is they can be very large, it can be very large, and let us say you have a voltage supply of, let us say you have a voltage supply of 5 volts, you are not going beyond that. So if these transients are very large, it might burn your circuit. So we want to analyze it, because it can go beyond 5 volts, like it can go up to, let us say, 7 volts or 8 volts. Then what will happen? It will burn your circuit or not? Because your circuit is only operable at 5 volts. So we want to analyze that what is the maximum it is going and how it is behaving with the voltage source. Sometimes it happens that your circuit will diverge, it will be like this, it will be like this, and it will keep on diverging. So the voltage amplitude will become very large and it will become unstable. So we want to study that whether this circuit which you are actually working on is stable or not when you apply this switching action. So we want to study the stability. If the circuit is stable, it will give you some fluctuations, but then it will settle down. But if it is unstable, then it will keep on jumping around, and it will create a very large amplitude which may burn your circuit. Okay, so that's why we want to understand the transient part, because this is a troubling part. We want to understand whether it's controlled or not. Okay. Any other question? Okay, so let me close this class today, as it's already past 9:45. Thank you so much for attending the class. In the next lecture, we will study more about it. Okay? Thank you.
Thank you.
Okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay.
Thank you, sir.